Okay, this is the extraterrestrial life lab. This one's a little bit different um, because this is I've incorporated this into a lab from a talk that I've given at several universities. Oh, wait, we don't. Why is that doing that? I have multiple monitors. I do not know why. This is. Okay, so again, a little bit different. It's a little bit more fun. I really enjoy this lab. So here's you. You're Fry from Futurama. And you live on the planet Earth, right? And Earth is one of eight, nine, if you want to go that far, but eight planets in our solar system. And our solar system is just one blip of a pixel in a galaxy that looks, uh, well, in the Milky Way galaxy, which looks fairly similar to this. And that galaxy itself is one of hundreds of billions of galaxies in a vast universe. So, what we're going to do today is figure out what you're going to do today, I guess, is figure out how many uh, civilizations may be residing in our galaxy. Okay. So, this isn't even about the whole universe, it's just about the galaxy. And multiply whatever number you get by hundreds of billions, if not infinite, because we don't know that the universe is or is not infinite. Um, and that's how many civilizations there are in the universe. So, overview. We have to talk about what is life. We're going to talk about Frank Drake, the guy that made this Drake equation. Talk a little bit about astrobiology. I'm not a biologist by any means, but it's what we're going to do. We're going to talk about Drake's equation itself, which is the point of the lab. And then we're going to talk about the search for extraterrestrial life and future plans. I do need to update this a little bit, but for the lab, for what we're doing, it's fine. So, what is life? Definition: the quality that distinguishes a vital and functional being from a dead body. That's what life is. It's a principle or force that is considered to underlie the distinctive quality of animate beings. And more often than not, this last one is uh, fairly fairly reminiscent of what we think of like actually what life is. An organismic state characterized by capacity for metabolism, growth, reaction to stimuli, and reproduction. So metabolism, you eat things and you metabolize it. Growth, reaction to stimuli, you poke something, it flinches, something like that. And reproduction, it reproduces things. So Frank Drake, there he is. He's still alive as far as I know. He's a very old man. He was born in 1930. 1958, he got his position at the National Radio Astronomy Observatory in Green Bank, West Virginia. In 1960, he uh, named Project Ozma, which was a 2 week search observation of the stars of Tau Ceti and Epsilon Eridani. They did not think that they would find anything, but hey, you have to start somewhere. I don't know why they picked those two stars actually, but um, got to start somewhere to look for life outside of the world, and that's kind of where they where they picked, and they did not find anything, obviously. Okay, some astrobiology is the study, origin, evolution, distribution, and future of life in the universe. There are 4 questions. How does life begin and evolve? Is there life beyond Earth? How can we detect it? And what is the future of life on Earth and in the universe? Astrobiology, very booming field in science, as you can imagine. It's a joke. Pre-Genesis. So, we're not going to talk a lot about this, but how might life arise on a planet? There are two main theories. We have comets or meteorites, or abiogenesis. So there's a famous experiment called the Miller-Urey experiment, showed the creation of organic amino acids, which are the precursor to life. Basically, what they did was they put a bunch of chemicals that they thought that they think is what the early Earth represented in a big jar. Essentially, I mean, it's much more complicated than that, but just to boil it down, they just recreated very very early Earth, and they left it. They basically, it's like a pot of stew. They left it for a while and came back, and they found these organic amino acids, and amino acids are precursors to like DNA and things like that. So RNA and other things. So um that was a very very big experiment at the time. The two main theories, comets or meteorites, um that is the idea that we got our life from comets and meteorites because we have also found organic amino acids in comets and meteorites. But that doesn't really explain where life came from. I mean, it does in to the relation of Earth, but it doesn't really explain how life would have originally come about, right? So abiogenesis, that is talking about if you have just the right conditions and just the right places on Earth with these amino acids, and let's say, I don't know, lightning strikes or you infuse energy into the system in somehow, in some way, excuse me, then life will spontaneously arise. So the big question is like, when is life life? And that's something that I'm not here to say because I'm not a biologist by any means. Um, but it's something really interesting to look at. Okay, Drake's equation. This is what you need to know. This is what we're doing for the lab. Okay, let's do at the end of next week. And I'm going to go through all of these. You have the number of stars forming in the Milky Way, like our sun, so it's the rate of star formation. You have the fraction of those stars that have planets around them. You have the number of planets per star that's capable of sustaining life. Then you have the fraction of planets where life evolves. And then you have the fraction of those planets where intelligent life evolves. And then you have the fraction of those, so you have intelligent life that can communicate. And by communicate, we mean like send radio waves out into space. Okay, not just like talk to each other. And then from those, this is the most interesting one, which is the reason why I do this lab. The fraction of the planet's life during which the communicating civilizations live. Okay. So, the rate of star formation. How many sun-like stars is the Milky Way producing? And why is that? Well, if a galaxy isn't active in star production, we're probably at the end of the galaxy's lifespan. Um, let's say that you have like a planet, you go down on the planet, and all you see is old people. There's no young people, there's no babies or anything. Well, that planet's probably about to die, right? Like, so we estimate this to be about 7 per year. So what I want you to do is to come up with your own numbers. Now, these first few numbers you can use from me, okay? The last few numbers, the last, let's say three numbers or so, I want you to give your own opinion about that. And by opinion, I mean I want you to go and search online and tell me why you chose the number that you chose. So you can use 7 on this one. Okay, you can use 7 because that's a fairly standard recognized astronomic number. Okay, fraction of stars that have planets around them. There's King and Kodos there. Um, with the star formation, the solar system, and everything like that, it's unlikely that all of the material is used for that star. Search for extrasolar planets is an exploding field of astronomy. I personally did my thesis on exoplanets. We're constantly developing better optics to measure these planets. Estimates place this number about 25% of sun-like stars have planets around them. When I made this was true. Now, this is not true. It's much higher. So you can use a much higher number. Go on the internet and search out what this number might be. I do, like I said, I do need to update this, but if I were to give you a ballpark estimate, I would say probably 90% of sun-like stars. That's how much astronomy has come from 2012. It's absolutely insane. But if you put 90%, you you need to find a source or something like that. Don't just put, oh, my teacher said that or my professor said that. Okay. I'm throwing out a number off the top of my head, but it's probably most stars have a planet around them, unless it's like a binary star system or something. Okay. Number of planets that are capable at sustaining life. So this is where we become more uncertain at this point. Drake assigned a value of 2, so 2 Earth-like planets. Maybe Earth and Mars, maybe Earth and Venus. We definitely know Earth is one. So you could also get super in depth with this as well, because this is just a very basic equation of Drake's equation. I mean, we're not even talking about like moons around other planets. For example, like Europa may have life, right? Like because it has water under its crust. So we don't know. Okay? Like it would not be unthinkable to even put like 3 or 4 here. If you want to call like a moon, quote unquote, a planet in this context, right? So, or I mean, you could go as low as 1. Just say there's 1 planet per solar system that could harbor life. It would have to be in the Goldilocks zone like Earth is. It's up to you. There is no right or wrong answer here. Does life require an Earth-like planet? Is liquid water a must? Water is a universal solvent. It carries nutrients throughout the bloodstream. So, current estimates place this value at 50% whenever I made this. That is 2 for every 2 star systems. One of them has a habitable planet of which life can arise. And that is just a best guess. I mean, for all we know, like right now, we are the only planet that can harbor life, but that doesn't mean that there aren't other planets. The universe is a very, very big place. So, oops. Okay. So it's up to you. It's whatever number that you want to put based on whatever research that you have. Okay, so the fraction of planets where life evolves. So how likely is life to arise given a habitable environment? So let's say that you have a planet that can sustain life, how likely is that to actually have life on it? Okay. So right now we're leaning towards the fact that life will occur given the right conditions. So this is basically 100% or 100% equals 1 in your vast Drake's equation. So we have organic material in space via interstellar molecules, as well as meteorites containing those molecules. Water has been discovered on other worlds, such as Mars. Most importantly, though, is the discovery of extremophiles. You've maybe heard of tardigrades, water bears that can survive in the vacuum of space. Life, if it wants to survive, I mean, maybe not us. We obviously can't survive in space, but life is so diverse and so willing to continue that, yes, I say, maybe you disagree, and it's fine. It's totally fine. But I say that if there is a chance that life can come about, then it will. Scientists suggest this number is at 100%. That is, life will occur given the right ingredients in the right location. You can dispute that, and I'm curious to see if you will. But 100% right now, or a 1, like I said in your Drake's equation. Extinction events. Okay. So extinctions are a boon for intelligent life. That sounds like an oxymoron, but hear me out for a second. We have something called the Cambrian explosion. Something very, very bad happened several million years ago, and it wiped out most of life. But the ones that did survive evolved to fit the niches of all of those animals and plants and everything that got wiped out by whatever catastrophic event happened. So that is what's called the Cambrian explosion. It we had crazy creatures going around then. Of course, not most of them died out. They didn't make it, but life likes to experiment quite a bit, and we've had all kinds of alien creatures come down, or not come. Okay, alien by the fact that they look just absolutely insane. They're not actually aliens, but um, point is, uh, Cambrian explosion happened. And we've had multiple events like the Cambrian explosion, but not necessarily exactly like that. There's been 5, arguably 6 major extinction events, 5 for sure, where we've had a mass die out. The last big one was the dinosaurs, or the non-avian dinosaurs. You could argue that we're going through the 6th major extinction event right now because of humans, because we are basically destroying the planet, I mean, there are species going extinct every day, because we can't control ourselves. So, there have been 5, maybe 6 major extinctions. Several mass extinctions are recorded in fossil record. That means that, we have fossils as we dig deeper and deeper, and then those fossils stop. And then we have a different kind of animal that comes about. So, uh, yeah, those are extinction events. There are 5 major extinction patterns that are recognized. Like I said, there are people that are arguing that we're going through a 6th one right now. Extinction strikes both land and sea. On the land, animals suffer repeatedly. Plants tend to be highly resistant to mass extinctions, due to their morphology. Their plants plants have a different physiology than us. Obviously, they're more resistant to a lot of things. So there are preferential disappearance of tropical forms of life during mass extinction. So if you get up to the poles, either the North or South Pole, you're going to find hardier animals. In the tropical areas, like the rainforest and stuff, you're going to find animals that are just so specific to where they live that, anything can just wipe them out. It's just, I don't know. It's crazy. Tendency of certain groups of animals to experience them repeatedly. So if you have an animal that, I don't know, that re-evolves or evolves with a oh, what's the word I'm thinking of? It evolves in a like a common denominator type of way. That animal will endure. I mean, like crocodiles, for example, they've experienced several mass extinction events. Crocodiles are a very old species. Um, Alleged equals spacing or periodicity in geological time. We experience a extinction event every about 26 million years. Of course, this is an average. Sometimes it happens quicker, sometimes it doesn't. And there's a lot of reasons for it. An extinction event isn't just like a meteor or a comet or whatever hitting Earth, meteorite hitting Earth. There are a lot of different reasons for that, but it's fun. So the point of all this extinction event talk, is we need to figure out the fraction of life where intelligent life evolves. So if we have life, does intelligent life come from that? So you have life, you have like microbes and stuff. We're talking about intelligent life now. How often does life in general serve as a precursor to intelligence? So I use Carl Sagan. The adaptive value of intelligence is so great, at least until technical civilizations are developed, that if it is genetically feasible, natural selection seems likely to bring it forth. You can use this if you want. I'm not saying you can't, but this is just what I found. There are a bunch of arguments for this. Scientists are divided between 10 and 100%. I put 100%. So my personal feelings on this, and this is where science gets a little bit of art here. I mean, you have to think critically and rationally. But if you have two competing life forms that are quote unquote not intelligent, but one develops a horn and another develops a shell, and then the guy that has the horn develops a bigger horn or a sharper horn, and then you develop a bigger and sharper shell. It's an arms race all the way up. You're developing, maybe intelligence to go for the underbelly or something like that. Just, it's an arms race of all of this life stuff. So I set it at 100%. If you don't want to, that's fine. Just give a reason why. Fraction of intelligent life that can communicate. Okay, so now we've got intelligent life, which does not necessarily mean intelligent like you would think of it, but intelligent, I mean, we have a bunch of intelligent life here on Earth. Humans probably not among them, honestly. I mean, dolphins, cats, dogs, any mammal really is intelligent. It's just what portion of those species can communicate. Of course, we humans are the, you know, ideally, or the most intelligent, quote unquote. Maybe not always, but um, dolphins, like I brought up. Dolphins are very intelligent creatures right behind us on the food chain. I mean, dolphins can communicate with each other. Of course, they can't build anything, but um, it is generally thought that technology could only occur on dry land. That's because if you have any kind of technology built underwater that can communicate, what's going to happen is that you have to get through the medium of water, and then you have to get through the medium of air, and then you can go and broadcast your signals into space. So, any technology that's developed is probably going to be on dry land. Now, you can disagree, you can make some arguments maybe against that. I don't know really how you would, but you can. Um, but but this is what I argue is that technology would be on dry land. The most accepted value is about 10%, a rather conservative number, but not zero. Why is it not zero? Well, we know that it's not zero because we exist. None of these items can be zero because you are listening to me right now talk about all of this. Okay. So this is the most interesting one, and to be completely transparent, it's why I do this lab because I love reading everybody's responses to this. Uh we need L, which is a fraction of the planet's life during which communicating civilizations live. It's the most misunderstood of all the factors. Do intelligent races destroy themselves before achieving communication? Or right thereafter? If a race has achieved interstellar communication, how long will that species last? Estimates vary between 100 years, that is assuming the race self-destructs near a human-like technological state, to several billion years, surviving as long as the host star. I estimate 1,000 years. Drake estimated 10,000 years. So this is what I want you to do. How long do you think the human civilization will last? This is the most up in the air question. You don't need a source for this. It is your feelings, and I am very, very eager to know what you think. I estimate 1,000 years these days. That is way too much of a generous estimate. I don't know. These days, I might put it at another 200 years or something. And this is from when the intelligent life can communicate. So we started communicating basically in 1900. Let's just call it 1900, right? Like radio waves and stuff like that. Right? Humans have been around for a very long time, but how long have we been communicating? Well, technically, if we say 1900, maybe late 1800s, but just for clarity's sake, let's say 1900. We've been doing it for about 100 years, give or take. I estimated 1,000. I was very optimistic at that time. Maybe not so much. Drake thought humanity would go on for 10,000 years. What do you think? What do you think? So, my results after we put everything in. So, here's the equation 7 stars per year. How excuse me, FP. FP was a fraction There it is. Fraction of stars that have planets around them. Yeah. Oops. It was 25%, 0.25. So I said like every 4 stars have a planet around them. This would be much higher if I were to do this today. This would be like 0.9. The number of Earth-like planets or planets where life can evolve. I said 0.5. So every star that has planets around them, 1 out of every 2 of them would have planets. So that's 0.5. So, okay, you have your stars, and then 25% of them have planets, according to this. And then of those that have the planets, 1 out of every 2 will have an Earth-like planet, assuming that's what we need for life. Then the fraction of planets where life evolves, I said 1. So if life can evolve on that planet, it will. Intelligent life. So if you have a planet that life can evolve on, what fraction of those will have life that is intelligent? I said 1 or 100%. Fraction of those that can communicate. So if you have intelligent life, how many of those can communicate? I said 10% or 0.1. And the lifetime of those species that can communicate, I said 1,000 years. So this is the lab, okay? The lab right now, this lab that you're turning in at the end of next week, you're filling in these numbers. And I want you to give me a reason why. So you're going to submit like a text document to me for each of these particular numbers. Now, you can do the rate of star formation. That's fine. You can put 7 down there. But for everything else, I want you to find your own numbers and tell me why. Okay, that it's just as simple as that. There's no right or wrong answer here at all. It's just a thought experiment. So whenever I do that, I say that there are 88 civilizations here in the Milky Way right now. Of course, we have not. The Milky Way is a big galaxy. Okay, so I mean, we don't know. Like we just don't know. But that's just my estimate. And think about this: there are hundreds of billions of galaxies in the universe that we can even just see. It may go on for much more than that, right? That's just what we know of, the observable universe. So, there are 88 planets within our galaxy that have intelligent and communicable life. I'm going to stop it here because there's another about 10 slides, but it doesn't really matter. Okay. I want you to give me your numbers in all of these variables, and I am just so curious, especially on the lifetime. I want to see how optimistic or pessimistic you are. It's I don't know. It's just a wild thing for me to read these. I love this lab. This lab is so good. Um, but yeah, so for all those watching, the point of the lab is to give me the number of civilizations that you think are alive and well in our galaxy right now, 88, and I want you to give me reasons for each number. So that is the lab, and I hope you enjoyed doing this. It's a fun lab. Again, super simple and easy, but I think it's definitely worth doing. Drake's equation is a fascinating equation to me. All right, thanks for watching, and have a great Thanksgiving.